Okay, so this is for chapter 19. We're going to study aldehyde and ketones. The homework will be the typical the practice skills in 19.1 and 19.42. So both ketone and aldehyde functional groups possesses the carbonyl groups. Carbonyl is the C to O double bond, so carbonyl group. In aldehyde, at least one of the other two bonds bonding to this carbonyl carbon is H. In ketone, both of the other two bonds bonding to the carbonyl carbon is alkyl or some other carbons. They are both important in biology and industry. The simplest aldehyde used as a preservative is the formaldehyde. The simplest ketone used mainly as solvent is acetone. Many other common ketones and aldehydes. Here are examples: vanillin, testosterone, and so on. There are 4 discrete steps to naming the aldehyde or ketone. Similar procedures as with alkenes, alcohol, etc. First, identify and name the parent chain. Secondly, identify the name of the substituents, the side groups. 3, assign a locate number to each substituent. 4, assemble the name alphabetically. Identify and name the parent chain. For aldehyde, replace the E ending in alkane with Al. For example, butane for carbon. And if you have this functional group carbonyl with H at the end, then you will see this name will be butanol. And the parent chain must include the carbonyl carbon. So not only the longest, but also must include this carbonyl carbon. All right, so this longest chain in this example on the left or on the right, both are octane, contain 8 carbons. But to name this compound on the right, we will not choose the 8 carbon chain because that 8 carbon chain don't have the carbonyl. So we'll use this 6 carbon chain. So the parent name will be hexenol. Identify name the parent chain continued. The aldehyde carbon is assigned number 1. So we see in this molecular, we have the aldehyde and alcohol and alkene. So the priority will give to the aldehyde. So therefore, when we number the carbon, we will use 1 on this side. So therefore, 1, 2, 3, 4, 5, 6, 7. That's the longest chain. And then we will give the locate for all the substituents. For ketones, replace the E ending with ONE. For example, here is butane, and then this one is butanol. In this case, we don't have to indicating where is the carbonyl. It cannot be at the end. If in the middle, just in the second location. So the parent chain must include the CO group. The CO carbon is given the lowest number and can be expressed before the parent name or before the suffix. For example, this ketone, we can see this is 3 heptanol because this carbon near is on the third carbon. Or we can see heptane, that means we have a 7 carbon chain. Then this carbonyl on the third carbon is indicated by 3 on. The configuration of a chiral center is indicated at the beginning of the name. So for example, R, referring to this configuration is R configuration, and then 2 chloro, 3 phenol, so 2 and 3. So 2 we have chloro, 3 have benzene ring, which is the phenol, and the longest chain is 1, 2, 3, so propanol. Altogether will be this name. Aldehyde next to a ring is named as carbaldehyde. So here we will see this is cyclohexane, and this carbaldehyde, the name in red. Altogether will be cyclohexane carbaldehyde. IUPAC name also recognize the following common name as parent name: formaldehyde, acetaldehyde, benzaldehyde. And as a summary of how to prepare aldehyde, we can prepare aldehyde by oxidation of a primary alcohol. And here are some of those common oxidation agents: PCC, DMP, DMSO, are listed here in this slide. So when treated with a strong oxidizing agent, primary alcohol are oxidized to carboxylic acid. Formation of an aldehyde requires a mild oxidizing agent, such as the oxidizing agent shown above the name, and here are the structures. They will not further oxidize the resulting aldehyde. So the aldehyde and ketone can also be prepared from the ozonolysis of alkenes. Here's one generic equation. We have the alkene, the CC double bond with the ozone, and we can produce either aldehyde or ketones, depend on the substitution of this C and C in the double bond. So the ozonolysis will cleavage CC double bond if either carbon atom bears a hydrogen atom, and aldehyde will be formed. Another way to prepare aldehyde is using the hydroboration oxidation of a terminal alkyne, the CC triple bond. And so the hydroboration oxidation results in anti-Markov-Nikolov addition of water across a pi bond, followed by the tautomerization of the resulting enol to form the aldehyde. And we can also produce ketone or aldehyde use oxidation of alcohols. A variety of strong or mild oxidizing agent can be used to oxidize secondary alcohol. The resulting ketone does not undergo further oxidations. We can also use alkene ozonolysis. We saw that before. And here we see it produces ketone because this alkene is tetra substituted, so all the carbon here don't have H, and the result product will be the ketones. We can also use acid catalyzed hydration of terminal alkynes. This procedure resulting in the Markov-Nikolov addition of water, which means the water, the OH will adding to this carbon here, then we'll get an enol. So the enol tautomerize to produce methyl ketone. So in this ketone, one side of the carbonyl is methyl, come from this carbon here. We also learn the Friedel-Crafts acylation. So we can use aromatic compound, for example, benzene, aromatic ring that are not too strong deactivated will react with an ethyl halide in the presence of Lewis acid to produce an aryl ketones. So this will be the reagent and produce this aryl ketone. Carbonyl carbon is electrophilic. This is derived from the redness effect and the inductive effect. So we see if we think about the redness, so we have this carbonyl C2O double bond, and this small electronegative carbon can take all the 3 pairs and get a single bond between O and carbon resulting in the carbon cation. Always think of induction because the more electronegative oxygen atom just pull those electrons in the chemical bond closer to oxygen atom, make this carbon partially positive. The carbonyl carbon is attacked by nucleophiles, forming a new sigma bond in exchange for the CO double bond. In that CO double bond, one of them is a pi bond, and become a tetrahedral center. So this carbon changing from sp2 hybridization with a trigonal planar geometry into a sp3 hybridization and tetrahedral geometry. Aldehydes are generally more reactive towards nucleophile than ketone. Two effects. One is the steric effect. Aldehydes are less steric hindered because one side is a small hydrogen atom. Secondly, electronic effect. Aldehydes have a larger partial positive charge on the carbonyl carbon. Here, this relatively larger. Because ketone has two electron donating alkyl, the R groups that stabilize the partial positive charge, and aldehyde has only one electron donating alkyl, the R group that stabilizes the partial positive charge. So therefore, this partial positive charge, the delta plus in aldehyde, is larger than the delta plus in ketone. Some nucleophiles require acidic condition, others require basic conditions. Example, the Grignard require a basic condition. We know Grignard is some alkyl with magnesium and bromine. Generally, a strong nucleophile means the reaction is on the basic condition, the Grignard, hydride, etc. On the basic condition, all nucleophiles react with carbonyls by the same general mechanism. In this mechanism 19.1, nucleophiles addition on the basic conditions. So the first step is nucleophilic attack. Nucleophile attack the carbonyl carbon. The carbonyl group is attacked by nucleophile, forming an ionic intermediate. Here. Then the second step is the proton transfer. The ionic intermediate is protonated upon treatment with a mild proton source, example water. Nucleophile attacks forming a negatively charged intermediate, which is protonated upon acidic work-up. So this is the summary of the two-step mechanism. Aldehyde and ketone react with a variety of weak nucleophile on the acidic condition by the same general mechanism. So in this two steps of reaction, the first step is the protonation of the carbonyl oxidant or the proton transfer. The carbonyl group is first protonated, rendering it more electrophilic. So and the nucleophile attack the carbonyl carbon, produce the final product. The carbonyl is protonated to form a positively charged intermediate, which can be attacked by a weak nucleophile. Acidic conditions are required in order for a weak nucleophile to attack a carbonyl carbon. So protonation makes the carbonyl carbon more electrophilic, very powerful electrophiles. Protonation of the carbonyl makes a better electrophile. When a nucleophile attacks a carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a living group. For example, for this ketone with HCl, it was favored at equilibrium. So the reactant is favored. Since the nucleophile Cl1 negative is also a good living group, equilibrium favors the starting ketone. So you can think this addition and produce this product has Cl, but Cl is a good living group, therefore it favors the left side. We will cover the following nucleophile and their reactions with ketones and aldehydes go by the active atom, oxygen nucleophile, water, alcohol, diols, sulfur nucleophiles, H2S, diethyls, nitrogen nucleophiles, amine, as a primary amine, secondary amine, and the hydrogen nucleophiles. Pretty much they deliver hydride, which is H negative from this structure and this structure, H4Al and H4B. Carbon nucleophiles, for example, the Grignard or the cyanide, or this we will learn later called the elate. In the presence of water, a ketone aldehyde is in equilibrium with hydrate. So adding water to the carbonyl produces so-called hydrate, two hydroxyl on the same carbon. Equilibrium generally does not favor the formation of the hydride, does not favor that, except for very simple aldehyde. The rate of reaction is slow unless acidic or basic condition is used. On the basic condition, OH is the nucleophile, so this is the base catalyzed hydration. So base hydroxide, for example, attack the carbonyl carbon, produce the anion intermediate, and then abstraction, another proton from water, it produces this hydrate. Under acidic condition, the carbonyl is protonated, and H2O is the nucleophile. So once the carbonyl get protonated, it becomes very good electrophile, so therefore water can attack. So then deprotonation of this oxonium intermediate produce this hydrate. Again, hydrate means okay, so drawing the mechanism, keep the following in mind when drawing the mechanism. Under acidic conditions, a mechanism will only be reasonable if it avoids the use or formation of a strong bases. A strong base can't exist in an acidic environment. Under basic conditions, a mechanism will only be reasonable if it avoids the use or formation of a strong acid. A strong acid simply cannot exist in a basic environment. Alcohols can attack ketones and aldehydes to produce the so-called acetols or semi-acetols. Here's one total overall equation. So we, for example, we have a ketone and reacted with 2ROH, which is alcohols. In this example, under acidic conditions, so produce this structure called the acetol, which means there is one carbon bonding to two OR, kind of like a two ether group bonding to the same carbon, and also produce the side product water. Under acidic condition, one ketone aldehyde reacts with two alcohol to form acetols. Commonly used acid catalyst for acetol formation is this TSOH or the sulfuric acid. The mechanism is shown here in this slide. So first step is the proton transfer under acidic condition. So the carbonyl oxygen get protonated. So we have this oxonium intermediate. So the oxonium intermediate is attacked by the water, and so then we will have this intermediate. So this intermediate has this O with 2H and has a positive charge on oxygen. So then we can do the deprotonation and produce this so-called semi-acetol. So another proton transfer protonate this OH group here, then we can see this produce this intermediate, and then it can this oxygen from the same acetal can form a double bond, and then the water leaving produce this intermediate, and so now we will have another nucleophilic attack from water attack this carbonyl carbon and produce this intermediate, and then finally do another proton transfer, get this acetal. Acetal formation is an equilibrating process. For most simple aldehydes, the acetal is favored at equilibrium. So you can see here, and this is formaldehyde reacting with two ethanol, produce this product, which is favored at equilibrium. For most ketones, the acetal is not favored at equilibrium. For example, this acetone and its react with two ethanol is favored this side. We don't produce too much of this acetal. If a diol is used, then both equivalent of alcohol come from the same compound, and cyclic acetal is formed. Ketone and reacting with diol, so you can see produce the same acetal than cyclic acetal. Acetal formation is reversible and can be controlled by adding and removing water. To favor acetal formation, water is removed from the reaction. To converting an acetal back into ketone or aldehyde, water is added to the acetal with H+ catalyst. So here, to produce acetal, we take water out, just Li Xiaodai principle. And then to recover the ketone or aldehyde from the acetal, we adding water and adding catalytic acid. In this way, acetal can be used as a protecting group for ketone and aldehyde. Consider how the following synthesis could be accomplished. So we want to converting this ester into alcohol and keep this ketone intact. We need to converting an ester to a primary alcohol with required the hydride agent called LAR, while leaving the ketone unchanged. The problem is using LAR while reacting with the ketone as well. Solution is using protecting group for the ketone. So here we go. First, protecting the ketone as a cyclic acetal using this diol. And then we can reduce ester, and then we will deprotect the ketone. So overall will be this step one is protecting this ketone, produce this. Then we use LAR to reduce this ester, and we work up to produce this alcohol, and also deprotect this ketone. Semi-acetal is the intermediate formed in the conversion of an ketone aldehyde to an acetal. They are generally difficult to isolate, as equilibrium either favors aldehyde or ketone or acetal based on the condition used. So here is the process. We can see usually if we have this acetone and want to produce the acetal, so actually they always favor this side, and the intermediate is very difficult to isolate. The intermediate called the hemiacetal, we only have one RO, and we still have the OH group on the structure. However, cyclic hemiacetal can usually be isolated. A cyclic hemiacetal is possible when a compound contains both the carbonyl group and the hydroxyl group. And so this is a cyclic hemiacetal. It really actually favored at equilibrium. Cyclic hemiacetal are important in carbohydrate chemistry. like those sugars, for example, glucose open chain is not dominate, and the cyclic hemiacetyl glucose is dominate or favorite at equilibrium. Under acidic condition, aldehyde ketone react with primary amine to form imine. So we have this benzaldehyde, and at like acidic condition, reacting with this methylamine and remove water to produce this imine. So imine has this structure, carbon double bond to nitrogen, and nitrogen will have some other substituent like a methyl or some other alkyl group. The reaction requires acidic condition to work. The main structure here for the imine is C double bond to N. The mechanism is we, for example, using this acetone as an example. Acetone react with ammonia, and we produce this intermediate, and then we can protonate this intermediate, and so that will produce this alcohol group here. Then we will use a base to abstract this hydrogen to produce the carbonyl amine, and then proton transfer again, protonate the OH, and then the OH can become a good leaving group, and this lone pair electron on nitrogen come here to produce the double bond, and we have this structure. Then another proton transfer, use some base, take the proton away, and we finally produce this imine. Even though it is under acidic condition, protonation of the carbonyl is not the first step of imine formation mechanism. Imine are bases and consuming the H+ catalyst. The ammonium ion, so this ammonium ion is the acid catalyst for the reaction. The ammonium ion is not acidic enough to protonate an aldehyde ketone, but is acidic enough to transfer a proton to the negatively charged oxygen in the second step. The imine formation, the pH has to be right around 5, or the reaction is too slow. If the pH is lower, all the amine are protonated, non-available to attack the carbonyl. If the pH is too high, not enough acid to catalyze the reaction effectively. Under acidic condition, aldehyde and ketone react with secondary amine to form amine. So, for example, this ketone here under acidic condition react with secondary amine. Secondary amine means the nitrogen has only one H, and then the nitrogen is bonding to 2 carbons, and produce this amine. Amine, the structure is the N bonding to CC double bond carbon. The reaction requires acidic condition to work. The mechanism is identical to imine formation, except for the last step, as seen in this slide. So in the last step, because we don't have a hydrogen on the nitrogen, so the base will take a proton away from one of the carbon and produce this double bond in the carbon to carbon. Then the double bond between carbon and N is reduced to this lone pair. The reaction requires a acidic condition to work. The mechanism is identical to that. And here we see this comparison using a primary amine. So we will produce this imine, use secondary amine, and secondary amine we have a 2R group, only one H on the nitrogen. Then we'll produce this imine. Compare the structure here. Imine is carbon double bond to nitrogen, and amine is the nitrogen bonding to a carbon, the carbon is in the double bond. No double bond between carbon and nitrogen. Wolff-Kishner reduction is a two-step synthesis converting a ketone to an alkene. So we can see here this ketone using, for example, here is this like the some of those reducing agents produce this imine, then reacting with some base produce this alkene. First step is the imine formation between ketone and hydrogen, which is like a primary amine. Second reaction is like elimination. Mechanism for second step of a Wolff-Kishner reduction. So once we have this imine, and we can see we can use some base abstract this hydrogen and produce this intermediate, and then this intermediate will do some rearrangement of electrons, produce double bond between N and N, and reduce double bond of N to carbon to produce this carbon anion, and then this carbon anion is going to take H from some of those like solvent and produce this intermediate. Another proton transfer, so this proton is taken away by some base, produce this N to N double bond, and then this N has negative charge, and then this this negative charge nitrogen can produce this N to N triple bond, and then that becomes a leaving group, good leaving group, which means N2 gas. Then we will have this carbon anion. So this carbon anion finally abstract proton from water, produces alkane. Note the many similarity between the acid catalyzed mechanism we have discussed. One thing to always note, under acidic condition reaction, a species should either be neutral or have a +1 formal charge. Acetal and acetals are hydrolyzed with aqueous acid to yield a ketone or aldehyde and two equivalent of alcohol. Simply the reverse of acetal formation and has acetal and converting back into ketones. So those are the hydrolysis of acetals. Acetal will only react with water under acidic conditions. If we have basic conditions, then there's no reactions. And here the mechanism under acidic condition, so the acetal get protonated, and so then we can have see this will alcohol become a good leaving group, and so then we will have this nucleophilic attack from water and produce this like RO group, and in the same time the water is attached to this carbonyl carbon. Another proton transfer, so will produce this alcohol and RO group. Then we will have another proton transfer, protonate this RO, and then water come back and kick out this alcohol or loss ROH. So then we have this intermediate. Then we can take the proton away from this intermediate, produce the final ketone. Hydrolysis of imine and enamine undergoes a very similar mechanism under acidic condition. So under acidic condition, this imine will be converted back into ketone. This enamine under acidic condition also converting back into the ketone and recover the secondary amine or primary amine. The mechanism of hydrolysis for imine and enamine are simply the reverse of the mechanism of formation. Ketone and aldehyde react with the thiol virtually the same way, they react with alcohol. Thiol is RSH, alcohol is ROH. So here we have this thiol acetal, and we can also produce cyclic thiol acetal. Thiol acetal can be converted to alkene when reacted with renine nickel. So here's an example. We have this thiol acetal and reacting with renine nickel, and it's converting back into alkene. This allows for another method for reducing the ketone and aldehyde to the corresponding alkene. Glyceraldehyde and ketone reduced to alcohol with a hydride reagent like lithium aluminum hydride or sodium boron hydride. So this is called LAR. Function as hydride deliver reagent. So we have this, for example, this carbonyl carbon here, and we can use LAR. Then we work up with water, produce with alcohol. If you use like a sodium boron hydride, you don't have to use two steps. So the sodium boron hydride in methanol, that will one step reduce this carbonyl to the OH. These reductions are carried out under basic conditions. Hydride are strong nucleophiles. A basic condition, so the first step of mechanism is nucleophilic attack. So the hydride from those hydride reagent attack this carbonyl carbon. Lithium aluminum hydride LiAlH4 function as a delivering agent of hydride ion H negative. So we get this structure, then we have this negatively charged oxygen abstract proton. As a work-up step, acid is introduced into the reaction flask, and the alkoxide ion is protonated to Q1 alcohol. Recall reduction of unsymmetrical ketone forms a new chiral center. So here is an unsymmetrical ketone. We have two carbon on one side, one carbon on the other side. Reacting with the LAR and then work up with water, produce this racemic mixture of stereoisomers or enantiomers. Recall Grignard reagent attack ketone aldehyde to make an alcohol with a new CC bond. So here is one example of Grignard methyl magnesium bromide, and then we have to use two steps. So we will produce this alcohol. Then in addition, we have a new carbon-carbon bond here. So another example is this aldehyde and reacting with this methyl magnesium bromide is a Grignard reagent produce this alcohol, and this alcohol has this hollow center, so therefore it will produce a racemic mixture. Either phase of the carbonyl can be attacked by the nucleophile, and a new color center may result in this example. Recall the mechanism of the Grignard reagent is consistent with the basic condition. Grignard are strong nucleophile, strong bases. So the nucleophilic attack use Grignard actually deliver the alkyl negative one charged species. So the Grignard reagent function as a nucleophile and attack the carbonyl carbon, forming an alkoxide ion. And then as a work-up step, acid is introduced into the reaction flask, and the alkoxide ion is protonated to P1 alcohol. And here is the product. The cyanide ion is also a carbon-based nucleophile, and reversibly adding to ketone aldehyde to form the cyanohydrin. Cyanohydrin is this part of the structure has this C and then C to N triple bond. Then on the same carbon has the CN group, but also have the OH group. This reaction works better under basic conditions, and so catalytic amount of base is usually used. Mechanism of cyanohydrin formation under basic condition is shown here. We have this carbonyl group here. So it's a nucleophilic attack from this carbon in this cyanide ion. So the cyanide ion function as a nucleophile and attack the carbonyl group, produce this alkoxide. So that this alkoxide will abstract H, produce this so-called cyanohydrin. Acidic workup is not necessary since HCN serve as a source of protons. To achieve basic condition, KCN is usually added along with HCN. In this way, there is more CN cyanide than H plus. So for example, we take this acetone and use HCN, then use also some amount of potassium cyanide to give a lot of cyanide ion. And similarly, this benzaldehyde, so we will, in both cases, will produce this cyanohydrin. And for this second example, this carbon is chiral center. So the product in the second example is the chiral, and it has 50-50 chance the cyanide attack the carbonyl carbon from the front or the back. We have a 50-50 mixture of the two enantiomers. So we have the so-called racemic mixture for the product. Installation of cyano group is advantageous because it can be converted to other functional group. And here are two examples. Once we have this hydrocyano functional group here, it can be reduced. This cyano can be reduced into amine or can be reduced to carboxylic acid. Another reaction that is very interesting for ketone and aldehyde is the Whittaker reaction. The Whittaker reaction is an extremely important reaction in organic chemistry, like a Grignard reaction. In that sense, the carbon skeleton is modified. Ketone aldehyde is converted to an alkene with the formation of a new C double bond to C those structures. Here are two examples. So we have this a generic equation on the top, which is the carbonyl carbon. We use this called the Whittaker elate. It has this part will be wasted. Then what adding on to the carbon is this C and H and H. So the CHH replaces oxygen in the carbonyl part of the molecule. The Whittaker reagent is a phosphorus elate, in which a carbon atom acts as the nucleophile. So because of the electronegativity difference, and we can see this carbon will be the nucleophile. Elate is a neutral compound that contains a negatively charged atom adjacent to a positive charged heteroatom. So we referring to hydrogen carbon as a common atom in the molecule. Other than that, so all the other atoms are the heteroatom. The mechanism is likely a 2x2 cyclic addition between the Whittaker reagent and the carbonyl group. We'll see in this slide. So the mechanism is this elate react with the carbonyl carbon to O double bond, react with the carbonyl in the cyclo addition, produce this intermediate, and then fragmentation takes place. So we'll have this resulting products. the formation of the especially stable, this guy called the triphenyl phosphine oxide byproduct drives the equilibrium to favor the formation of the desired alkene. A given Whittaker reagent is synthesized in 2 steps from the corresponding alkyl halide. So if you want to add in that carbon, 1 carbon, you are starting with alkyl halide like methyl halide. So these 2 steps produce this Whittaker reagent, which has the resonance structure. The 2 step is the first step is SN2 reaction, and we use this triphenyl phosphine and phosphorus atom for acting as the nucleophilic site, taking the carbon, push the bromide out. Then we can use some like alkyl lithium and abstract the hydrogen, the proton, and to produce this elate. Whittaker reaction is particularly useful because it installs a C2C double bond at a specific place, the carbonyl carbon. And the Whittaker reaction is stereo selective. Use a Whittaker derived from simple alkyl halide, the Z alkane is favored. All right, so here we have this carbonyl, and we install, in this case, we'll install like 2 more carbons. So we're cutting this double bond here, then this O cut off. So we have this CC double bond, and this double bond here, because on both carbon there are different atom of blue purple atoms. So we have the larger methyl, the larger phenyl on the same side of the double bond. So those kind of structures are Z isomers, and this will be the major product. And if the Whittaker reagent contains the electron withdrawing group, then the E alkane is the major product. So here we will see this is the elate. It has the electron withdrawing group, that's CO2 ET. Then as a result, so this E configuration is the major. And another example is this elate, and we can see the same result. It produces this E configuration. An electron withdrawing group or a phenyl ring delocalizes the anionic charge of the Whittaker reagent, stabilizing it. And on the Wadsworth Emmons, called the HWE reaction, employs a reagent similar to stabilize the Whittaker reagent and also yield E alkane as the major product. So here's one example. Compare this Whittaker reagent with the electron withdrawing group and this HWE reagent. And you can see here this phosphorus atom is double bound to O, then 2 methoxide, and here is a 3 phenyl bonding to the phosphorus atom. Example of HWE reaction, and we are going to install this part like these 2 carbons with carbonyl and ester onto this carbonyl part, and you will see this E configuration as the major product. The HWE reagent gives E alkane as a major product, like a stabilized Whittaker reagent does. Choice of solvent and use of loose acid can also affect the stereo selectivity of Whittaker and HWE reaction. Re-choose synthetic analysis reverse two possible routes to make a given alkene via a Whittaker reaction. For example, we want to make this alkene and the target molecular, or we can see this the double bond cutting. Then we can see maybe will produce this target molecular from this ketone and this Whittaker reagent. Or we can think of we'll use this carbonyl group, and then we will use this Whittaker reagent. To determine which route is better, consider the LPL halide needed to make each of these two Whittaker reagents. Re-choose synthetic analysis reveals two possible routes to make a given alkene via Whittaker reaction. So in route 1, we need to install the CH2 group. So therefore, we're thinking of using methyl halide. And so then in this reaction, and we will see the first step is nucleophilic attack. And nucleophilic SN2, obviously, if you have a methyl halide, is better. So therefore, route 1 is better since SN2 reaction with methyl halide is better than with a secondary halide. So here we want to produce Whittaker reagent. We need to use this alkyl halide, which is the secondary alkyl halide. It's a little bit difficult to go with the SN2 reactions. And overall synthesis of the alkene via the Whittaker reaction for that last problem will be we use methyl iodide, and then we produce this elate, and then we add it onto this butanol, and we produce this alkene. Baeyer-Wallinger oxidation is an oxidant is inserted into an aldehyde or ketone between carbonyl carbon and a neighboring carbonyl group. So here is the carbonyl carbon, and we use some of those peroxide, and we can install an oxygen in between this carbonyl carbon and this alkyl. Aldehyde or ketone is converted to an carboxylic acid or ester respectively. So that means aldehyde will be converted into acid, and ketone will be converted into an ester. There's a mechanism here. The first step is the nucleophilic attack. So the peroxy acid function as a nucleophile and attack the carbonyl group. A proton is transferred from one location to another in the same molecule. This step can occur intramolecularly because it will involve a 5-membered transition state. And then we will have the rearrangement. The carbonyl group is reformed with a simultaneous migration of an alkyl group. So this alkyl group here are migrate to this, and then we have the two products. Cyclic ketone produce a lactone, and that is a cyclic ester. So you can see here we have this cyclic ketone has 5 carbon ring. We use peroxy acid, inserted oxygen between this carbon, this carbon. We have the so-called lactone. For an aldehyde or unsymmetrical ketone, the rate of migration is as the following: H rather than tertiary or phenol rather than primary and rather than methyl. So use this trend to determine the residue selectivity. And here we see we have this ketone, and we can either insert this oxygen in here between this carbon, or between this and this. So then we see this carbon here is more favored, so therefore we have this product, which means the oxygen is inserted on the left, not on the right. And then if we have a hydrogen, so hydrogen definitely favored than this benzene ring. So therefore, we will insert oxygen between this carbon and this H, produce this acid. Recall the question we asked when designing a synthesis. Is there a change in the carbon skeleton? Is there a change in the functional group? One of these reactions will be needed when the carbon skeleton is changed. So here are a summary of what a reaction can use to change the number of carbons. So we can either use Grignard and adding more carbons, or we can use this addition of cyanide and produce so-called cyanohydrin, or we can use Whittaker reaction. You should be able to make a list of products that can be made from aldehyde and ketones and identify the reagent needed in this. Then we can see the spectroscopic analysis for the aldehyde and ketones, and we will have a strong peak for the C2O stretching in the IR spectra. Then we can see that if we have conjugation, the conjugated carbonyl stretch, it will be at a lower frequency or wave number. Increasing ring strain increase the wave number. So the cyclic ketones, 6-member ring and 5-member ring and 4-member ring, and we can see the wave number or the frequency increases from 6 to 4. Aldehyde also give weak peak around 2700 to 2800 centimeter inverse for the CH stretching. And here is the example of the IR spectra. And for this aldehyde, then we can sign this these two peak somewhere about 2700, 2800 due to the carbonyl carbon to the H bond stretch. And this signal here, it will be the C2O double bond stretch. Protons neighboring carbonyl are weakly deshielded by the carbonyl group and appears +1 ppm downfield. And so this, we can see this compare as this C2 in the alkane, the chemical shift approximately 1.2 ppm. Now the nearby carbonyl and downshifted the chemical shift by approximately 1. So 1.2 ppm becomes 2.2 ppm. Aldehyde ketones are strongly deshielded around 9 or 10 ppm. So we see this proton in this carbonyl group in this aldehyde is really downshifted to downfield in about 10 or 9 ppm. So 10 ppm here, 9 ppm here. Carbonyl carbon produce a weak signal near 200 ppm. So this, for them, this carbonyl carbon here produce a weak signal. It's about 200. This is a review of chemical reactions with carbonyl. So this end of chapter 19.